All right, I think we're ready to get started. First, given how large the audience is, I have to ask, are you all aware this is a talk about DNS? Yeah? Okay, first I'll just briefly introduce the three of us who will be speaking. My name's Cricket Liu. I am the Chief DNS Architect and an EVP of Engineering for a company called Infoblox. I also was one of the co-authors of a book called DNS and Bind, which is a blue and white book with a grasshopper on the cover. Until recently, I thought I was the co-author of all of O'Reilly's books on DNS, but apparently they slipped a new one in there that I had nothing to do with, so I'm not. And this is Francois Tur, who is one of our senior software managers at Infoblox and one of the maintainers of CoreDNS. And we also have up front here John Belamaric. And John is a senior staff engineer for Google. He did work at Infoblox up until recently, and he's also a CoreDNS maintainer. So here's our agenda today. I'll give you guys a really brief introduction, 5 more slides, something like that. And then John will come up and he'll talk about the cluster default configuration for CoreDNS. We'll look a little bit at some non-default configurations as well, and we'll give you pointers to more resources. And with any luck, at the end, we'll have a little bit of time for Q&A as well. And we have, I think, mics in the aisles so that we can actually hear you. So let's talk very broadly about CoreDNS. First of all, it's a flexible DNS server. It's written in Go, so you get some of the advantages of Go right off the bat. You get a memory-safe executable, which is a big deal in the world of DNS, because if you're running a name server that's directly exposed to the internet, you want to make sure it's not vulnerable to things like buffer overruns. If any of you have run Bind, for example, over many years on an internet-attached host, you know that there have been lots of buffer overruns over the course of time that it has fallen victim to. Unfortunately, being written in Go also means that the top-end performance is not quite as good as, say, Bind running on a modern Linux operating system, right? But that's typically not an issue because we don't really use CoreDNS in applications where we need to get really, really high performance. It uses a plugin-based architecture, which is easily extended. John actually has a talk later on where he'll actually go into some of that. You'll learn a little bit about writing plugins for CoreDNS. Even if you're not somebody who would be interested in or capable of writing a plugin, have no fear. There are lots and lots of plugins available to perform all kinds of interesting functionality, and there are more being written all the time. One affirmation, actually, of the plugin architecture is that Bind is actually moving to a plugin architecture. So the great granddaddy of DNS servers is actually going to implement a plugin architecture as of Bind 9.15. CoreDNS supports DNS, of course. It's a DNS server. It also supports DNS over TLS, which we call DOT for short. And DOT is kind of the hot new technology in the DNS community. So if you want to play with the cool kids and set up your own recursive server that can do DOT and use your Android P device in order to send encrypted queries to it, then you can do that. Right. Also supports DNS over gRPC. And the project was initiated by Miek Gieben, who's a Dutch guy who lives in London, works for Goldman Sachs. And he also wrote SkyDNS and SkyDNS2, so he has experience writing, thanks Francois, writing DNS servers. He also wrote what is probably the most popular DNS library written in Go. And he looked at the Caddy web server, and I think he admired its architecture and decided, gee, you know, I have a Go DNS library. I could easily use this framework in order to develop a DNS server. And that's really what CoreDNS is. So, as you know, we have native support of Kubernetes service discovery in CoreDNS. CoreDNS went GA with Kubernetes in version 1.11, and as you probably heard during the keynotes yesterday, it's now the default DNS server in 1.13. It boasts all kinds of integration with etcd and other cloud vendors. For example, if you use Route 53 within AWS as an authoritative DNS server, you want to pull authoritative data into CoreDNS and republish it or simply use it in order to resolve, you can do that. And it does so via the Route 53 APIs, so you don't even need a direct UDP path to the name server that you're resolving to. It has support for Prometheus, for metrics. It also is capable of forwarding to a recursive DNS server, and this is important because it doesn't actually have the capability to act as a full-service DNS recursor itself. So it has to rely on another name server to do that. Or you can use some optional plugins, some out-of-tree plugins. We have one called Unbound, for example. Right. So you may be asking yourself, why CoreDNS versus the old kubeDNS? And there are a number of reasons. One is that plugin architecture that allows you to extend it very, very easily. The rich set of plugins, the rich ecosystem that's available to you, about 34 plugins as of this date, and new ones being developed all the time. Right? It's simpler. It has many fewer moving parts than the old kubeDNS did. kubeDNS was, I think, 3 different executables. It was kubeDNS itself, it was DNS mask, as well as a sidecar application. And some of those were written in C, not in Go. Right? And there are a couple of other things that are maybe in the category of esoterica, but still worth mentioning. Customizable DNS entries. For example, if you want to add static DNS data within the cluster domain that's completely unrelated to the service discovery stuff, you can do that, which is a pretty powerful thing to be able to do. There's an experimental server-side search path feature that will actually speed up resolution, because what you'll find is that within a containerized environment, your containers have these really long search lists that they're going to go through to find a particular domain name. And CoreDNS can actually anticipate that it's going to walk through all of the elements of that search list and match the first one rather than waiting till the 10th, for example. Here's the project status. We're at version 1.2.6. That came out about a month ago on November 5th. It's an incubating project within the CNCF. The graduation vote is either underway or just about to get underway. Is it actually underway?
The 1.3 next one.
Oh, I see, okay. Imminent. And a growing community of contributors, 112 contributors, all of whom we thank, 16 maintainers, 2 of whom are speaking today, 29 plus public adopters around the world. And if you do use CoreDNS, please, please, please add yourself to the adopters list, and over 3,000 stars on GitHub. And with that, I'll turn this over to Francois.
Thank you. Thank you, Cricket. So I will try to present now how it looks like in Kubernetes, the CoreDNS configuration for Kubernetes. We'll do that in 2 steps, 10 minutes about really the big picture of Kubernetes, how the query are resolved in CoreDNS, and how then we can tweak the configuration for some easy change or easy tweaks. And then John will come after for more complicated option or take advantage of CoreDNS more deeply. So our configuration right now is CoreDNS is the DNS server of a cluster. You have a Kubernetes cluster. CoreDNS is connected to the API of Kubernetes, so we can watch and listen the service, the pods, the endpoints. It just will resolve any query that aims to have an IP from the cluster, and will forward upstream every queries that are out of the cluster. Okay, so the pods are the one that query and say, oh, where is this service? Where is this service? Or where is this domain? So the domain can be inside the cluster or outside the cluster. This button. So first, let's look at when you deploy, when CoreDNS is deploying Kubernetes, what do you have? So you have a service account, a cluster role, a cluster role binding. That's very simple. And then you have maybe the more interesting part, the config map named CoreDNS. It's where reside what we call the core file. So you have a core file key with exactly the configuration for CoreDNS. So each time you will change the config map, this configuration will be pushed to all the CoreDNS pods that are running. Second, you have the deployment. So I highlighted here in the deployment what is a little specific. You have always at least 2 replica of CoreDNS. The labels, I will go to the labels later. First, the image of CoreDNS you have by default is located in a Kubernetes repository, which means it's not the the usual Docker Hub CoreDNS repository. Each time we qualify the image. Each time you have a release for Kubernetes, we qualify the image and push the image on the Kubernetes repository. One thing I wanted to say is CPU and memory. So the request of memory is 70 megabytes, or more or less. That is what was for kubeDNS. It's what you need. But you have to know that either kubeDNS or CoreDNS, we have to watch all the service. And the larger your cluster is, the more we will need memory. So when you hit 1,000 node, 2,000 node cluster, then you may have to tune your memory size. Okay, so it can go, the limit is 170, so we check that we fit into 170 if you go to a 5,000 node cluster. But depending your option, you may have to need more or less memory. Liveness probe, there is a probe that checks that CoreDNS is running, and if not, then the scheduler will automatically restart the pod. Okay, so that means the configuration of CoreDNS has to take care of that. And the DNS policy, because it's a problem we see on the support, is usually each pod of cluster has a DNS policy called first. That means it will call the name server. It will call CoreDNS as the regular name server, except CoreDNS, because you don't want CoreDNS try to call itself to resolve. All right. So that is for the deployment. And the last part is the service. Service is the same as before. It's even the same name. It's take kubeDNS. It is a DNS of Kubernetes anyway. There's no change from before, and that was expected like that. It is the DNS service anyway. So you don't want you won't see the change from kubeDNS to CoreDNS. Same service, and all the pods that resolve DNS will resolve for the cluster. Okay, what is the default configuration? So in the config map, you will have this information, which we call the Corefile. And I would like to go quickly over each of the items. So each item is called a directive, and it's a directive of a plugin. CoreDNS is based on plugin, and you just pile up all your plugins. So the most important is the Kubernetes one, the one that will resolve a Kubernetes request, that will resolve the zone of Kubernetes. The cluster.local, in fact, that is a sample, will be replaced by the zone you associate with your cluster. That means Kubernetes will resolve everything that is in the cluster. Load balance at the bottom, just say, if I have several reply for your request, I will try to simulate a load balancing by shuffle the order of the return records. All right, so that make an importance only for the headless service where you can have all endpoints will be replied. So okay, if you're cluster.local, then you will resolve your query with Kubernetes. If not, that means out of cluster domain. So it will be resolved outside by a proxy to an upstream name server. All right, and the list of name server is by default in etc.resolve.conf as it is on every pod or every machine. We have a cache 30 seconds, so that works mostly for the upstream DNS query, because Kubernetes will have a TTL of 5 seconds, in fact. Next one is a loop. A loop is just a very small plugin that detects that you have no loop in your resolution of queries. That happen sometime on some system. So it's something that just stops CoreDNS if we detect a loop in your resolution. You go upstream, that go back and come back. So we just send a query, and if it comes back, we say there's a loop. Health is the plugin that serves the liveness status, so you need it. In fact, health go down if Kubernetes plugin cannot connect to the API, or just the API disappeared, then the health go down, and the scheduler will reschedule another pod. Error is just enabling the logging of internal errors. Prometheus is to provide the metrics of Prometheus on the port 9153. And this one is an important one, reload. It allows CoreDNS to watch its own core file and reload the service if you change the core file, which means if you change the config map, then that will push the core file, and CoreDNS is watching its own core file and will reload. Take care, it will take about 2 minutes between the change on your config map to have the CoreDNS server reloaded. Okay, next thing. Before we tune the configuration, we need to work to see how CoreDNS behave and how it resolves a query. So I have on the left side, I have a sample of a core file. And on the right, I have its meaning inside of, in terms of organization of the processing of queries. So as you can see, on the left, you have 3 big parts, which we call the block server or stanza. One is organization.com, so it will match the left branch of this tree of resolution. The middle one, on-prem organization, the right branch, and the last one, the middle branch with a dot. Okay? So each time on the block server, you have a domain name and the port. You may, I mean, nobody wants in Kubernetes to change the port because DNS has to listen to port 53, else it won't work, or the pod has to send the query somewhere else. But by default, you will be on port 53. So how does it work is, on the tree, when the queries come in, so let's say we have a query, it will get into the tree decision by the top, and then we'll go into the branch depending the domain queried. It will try to match the more specific domain you are querying. So here, organization.com, the more specific would be on-prem, but that does not match. So you will go on the left branch, and will resolve your query going by errors, cache, and proxy. So it will be resolved by your proxy 133.3.4.1 for this one. If I take the next one, my DB on-prem, same thing. Let's say I push the query by the top. There is a decision on the tree, and it will go by the right branch because it matched the on-prem organization. It matched also the organization.com, but on-prem is more specific, so it will take the right branch. I try another one. mycompany.com. So at the top level, does not match organization, does not match on-prem organization, but it matched the point. Point means everything. So that will go by the middle branch, go down. Kubernetes cluster.local, it does not match the cluster.local, will go to the next resolver, proxy my company. Oh yes, it matched, so it will be resolved by this proxy. Okay? As soon as you hit a resolver, an orange plugin is a resolver, it will take care. If the resolver say, advertise on the top what domain I am resolving, and as soon as you match this one, the resolver will handle it. So they will not go down to any other resolver. Okay, last one, or next, up. I can go back up. This one, service cluster.local. So as you can see, will go central and will be resolved by the Kubernetes plugin. Next one, google.com. How does it work here? So at the top, it will go by the middle branch because of the does not match anything else. And in fact, does not match anything. So it will go by the last proxy dot because dot match anything. Okay. So it's how it works. It's just a decision of which branch I will go with my query. And then you organize your branch to process your query. Okay, so next slide. So the first configuration maybe you want to tune is, I have some stub domains that are not public. I mean, they will never be resolved by a public DNS resolver. Or I know that it will be resolved, but it will take a long time, so I would like to make a shortcut and just push to the right IP of the name server, of the authoritative name server for this domain. So you just want to create this block server you have on the log for corporate or local corporate and proxy to the right IP. Okay? So the way to write it is, okay, you add a block server with your domain and add a proxy plugin. Point means I match everything that will go into this branch, and I forward to the IP I provide after. You can provide several IPs in that. Oh, that works. Sorry. You can provide several IPs. In that case, there will be an automatic round robin between all the IPs. Okay. Next thing you may want to do is, okay, for a specific domain, I want a specific IP, but maybe I will also tune some other configuration. The first one is a cache, for example. By default, it is 30 seconds. For your corporate, you know it does not change too much. So you would prefer to have a cache of 1 hour, for example. You may want also to log some special queries just to monitor your queries. So in fact, that fixes, I don't know, 80% of the problem of people that want to tune in Kubernetes. After the 20%, I will let John explain what else you can do. Anyway, I went quickly into this proxy. Each one has a lot of configuration. Please go to the website of CoreDNS IO plugins to have a description and the list of options of proxy, of log, of error, of cache. You can do a lot of tuning on each of these plugins. Thank you. So, John, it's up to you.
All right, hello everybody. So I'll talk a little bit more of some of the things you can do that are outside the defaults, things that maybe aren't as common but might be interesting to people. A little bit about different options specifically within the Kubernetes plugin. There's also several other plugins that are really built specifically for Kubernetes, and then a few of these other use cases that Cricket mentioned in the beginning. So looking at these are the most commonly potentially changed options within the Kubernetes plugin. The first one here controls of whether or not we reply to the pod namespace. So normally the subdomain for services is svc.cluster.local. There's also one pod.cluster.local that's in kubeDNS basically just anything, any name you give it that looks like an IP address, it will reply with that IP, which is not ideal. So we have a few different modes. You can completely disable it, or you can have it actually only reply with the IP address of the pod if that's actually a pod in the actual namespace. Endpoint pod names will allow you to, instead of using some random numbers as the endpoint name in a headless service, it will use the pod name by default. And of course, you can change TTL. Fall through is interesting, and we'll talk a little bit more about that. That's a sort of internal way to allow more than one plugin to be authoritative on a given zone. There are a bunch of other options, too, that are not going to be as commonly used. These top ones here are really about how to connect to the API server. When you deploy it as Cluster DNS, which is really what this talk is about, that's not an issue because it's all done through the service account and all of that. But if you want to deploy CoreDNS external to the cluster for some reason, then you would make use of these options. There's another set of options around filtering or what we actually expose. So a question came up, I believe, in the intro about can we limit what we show to a namespace? Actually, we can. When you're running as Cluster DNS, that's probably not what you want to do in general, but there are some use cases around only exposing a narrow set of names. So you can do it with a label selector, you can do it with namespace, or both. There's also some little tweaks you can do on how the results are returned. Pod mode, these two we already talked about, as well as all of these. We also do support zone transfer. So you can, with your DIG client or with some other name server, you can initiate a transfer and get all of the cluster zone records into your other name server. It's also very useful for debugging if you're trying to figure out what records are there in CoreDNS. You can do a zone transfer just on the command line and see all of the options. So here are a few of the plugins. As Francois said, we sort of categorize these into a few different categories. There's plugins that just modify the configuration of the overall server. There's these middleware that manipulate the query and make some changes to it. And then there's the backends or resolvers that actually provide a source of data for resource records. There's actually a whole bunch more, and we have this whole deck as a PDF in the Sketch thing, and then you can follow these links and see the whole list of various plugins. One thing to note, this second bullet here, is that all of these plugins are, the default image compiles in a bunch of plugins. They're not plugins that you can load dynamically, they're compiled in plugins. So, and not only that, but the ordering is specific to compile time. So if you want to do something really different than most people, you may have to roll your own image. Okay, let's look at the other plugins that are, I'm just going to time check here. Let's look at the other plugins related to this. One of the most interesting is what we call Autopath. And there's, I think Francois or Cricket alluded to this a little earlier, that I think Cricket did. There's a lot of different long search path in Kubernetes. So when you go to make a query, you can use a name just like foo, and it'll check if that's the name of a service in the namespace of the pod that's making the query. If not, it'll it'll walk this whole path from namespace.service.cluster to service.cluster.local, cluster.local, and then all of the nodes search paths. So if you're in a cloud environment, sometimes that'll have regional names. There can be a whole bunch. So what you end up with, and this is one of the sources of a lot of issues, DNS issues in Kubernetes, is you can end up with making one query, one lookup. You're trying to find google.com, and it tries all of these different things. Now these are tried from the client. So the actual client makes a request to the server, gets a response, which is an NX domain, no such domain, makes another request, makes another request. Every single one of those is UDP, could time out, could be lost, could have a 5-second timeout waiting for it. So it can run into a lot of problems. Plus, it kind of pollutes the contract entries in the node. So we looked at this and we said, well, since we're already watching the Kubernetes API, if we watch pods as well as the other things we normally watch, we can take the source IP address of the client, look up the pod that belongs to and what namespace it's in, and then we can figure out what that search path actually is in the pod, all on the server side. So if you enable the pod's verified mode, which causes a watch on pods, and you enable the Autopath plugin, we will follow that entire path on the server side and then return what's called a CNAMer, an alias record that points to the real record. So essentially what that means in this case, instead of doing those 5 queries from the client to the server, you do the 1 query from the client to the server, and it returns a result immediately. So this is what this looks like. This is one of our users, actually a year ago, sent me this graph saying, hey, I enabled it, and all these, the latency dropped dramatically on all these requests to this S3 bucket or something. Well, so why wouldn't we enable this by default? And there's a good reason. The pod's verified adds load to your API server and adds memory to the actual CoreDNS instance. So if you've got a very large cluster, it's not advisable to enable that option. So for a default type of setup, we couldn't really do that. There's also a very strange edge case when you have caching enabled that you can sometimes get the wrong answer if you have services and endpoints and namespaces that have kind of colliding names. All right. This next one's really interesting. This is something we're working on. It's not done, but I think it's something people will be happy to see. We expect this to be in 1.3. The idea here is that normally for in-cluster DNS, the records that we are creating and returning are for those in-cluster service names, cluster.local. But of course, if we want to actually create a service that's usable by people outside of the cluster, then those are useless names. We have a lot of metadata anyway that we may be able to expose the load balancer IP addresses or the external IPs on the service directly to the outside world with another name. So that's what this plugin does. It piggybacks on the Kubernetes connection and allows you to specify a zone for which we should present all of these load balancer external IPs. You could run this internally with the same cluster DNS and expose that cluster DNS, or you could run a separate CoreDNS instance, which would be really the best practice to separate those out, since you've got external traffic you can't really control. And another comment on that, this is an unfortunate thing if you're using AWS or Google Cloud. I don't know about Azure, but the load balancers only support either TCP or UDP, and at least from Kubernetes configuration, which is basically kills using them for DNS without some manual intervention. So if you do want to use this, you might have to do some extra rules in your load balancers, not through the to expose this particular service, not to expose the other services, but to expose the DNS service. Do you have the time? How are we? Okay. Kubernetai. So this is an external plugin that you'd have to build out of, it's out of tree, you'd have to do a custom build for it. But this is something we built actually originally for Istio. I think they're using it. The idea is that we should be able to have the same name server talk to multiple API servers using, say, a different cluster zone and provide service for all of those. So if this can do a sort of poor man's federation, where you can essentially look up, you can be sitting in your cluster, and by using this plugin along with fallthrough, which you could have the same name, be responded to if it would ask for the local cluster. If there's nothing in the local cluster, it would go out to the next cluster and try and resolve that name. That works for headless services when you have routable pod IPs. Cluster IPs are not routable. That's why this isn't default or built in. It's kind of special purpose because cluster IPs generally aren't routable. Okay, two other ways to go about and make changes. I believe it was mentioned earlier that we could add some static data to the zone. And then there's a query rewrite, which has some interesting use cases. The adding static data, because CoreDNS is just a DNS server, and Kubernetes happens to be one of the things it does, it also serves zone files, and it serves, you can serve inline records right out of the Corefile using the hosts plugin. So this enables us to essentially override individual names if we want with the host plugin, or actually populate subdomains that are subdomains of the cluster.local but not normally part of Kubernetes. This is an example of how to do that with the auto plugin, which automatically loads zone files out of a directory. Another option that we think people may be interested in is query rewriting. So we saw this, the particular use case this really helps with is if you have an existing certificate that's got, say, a public name on it, but you want your in-cluster services to be able to access that in-cluster without going all the way outside, you can actually rewrite that name so your pod, your client in the cluster, uses the public name, The DNS looks at that public name and says, oh, that actually corresponds to this service over here, this internal name, resolves that service to an IP address, and then returns that IP address to the client. So things running inside the cluster using foo.example.com will get a cluster IP, and things outside the cluster using foo.example.com will get, say, a load balancer IP that talks into the service. So the same certificate can be used. So that's really what I wanted to discuss. So if we have time for Q&A, I'd be happy to answer any questions.
Thank you.